Let's continue our discussion on NetworkX library, following up on the previous video. In this video, we are going to try and do the hands-on on the NetworkX library. First, we have to import the library. If this library is not installed in your environment, then we will have to install it using either pip function or kunda function. The default is pip install NetworkX. This is a more widely used installation step. So this library is already installed in my environment, so I'm not doing it. But if you are doing it for the first time, please execute this particular function to ensure that the library is installed in your environment. Once it is installed, make sure that your kernel is restarted and then import the library. The NetworkX library contains a function called graph, which basically is an initialization function. It defines the object as a graph object, and we are labeling that as G. So we are kind of defining that we are going to create a graph, a network in Python now. And for this graph to start with, there are no nodes, no edges. Add node is a function which allows us to add a single node. So now, after this, the graph G contains a single node, which is 1. Okay, we are labeling that as 1. We can also add multiple nodes to the graph given this function, add nodes from. So I'm basically bringing in 2 more nodes into the graph. Next, in order to ensure that this becomes a graph, we have to also bring the second element, which is edge. And just like how we do add node, we have add edge. And here we are going to pass 2 nodes, which defines that there is a connection between these 2 nodes. Next, we are going to talk about another edge, which is 2 and 3. So I'm defining a tuple and labeling that as E. And using that E, I'm defining the edge for our graph. So you can directly define like this, or we can also give like this. So either way, we are going to try and create a tuple and pass that tuple for our graph. So now I have 2 edges. One is from 1 to 2, and now we are creating another edge which is between 2 and 3. We can also do multiple edges creation at a single function from a single function using add edges from. And here we have to pass an iterable object. Here as well, we are passing an iterable object for nodes. But here we will have tuples as the elements of those that iterable object, 1, 2 and 1, 3. So I'll also connect 1 and 2 and 1 and 3. So if you look at this graph, in total, we have 3 nodes and I have 3 edges as well, right? So node 1, node 2, node 3, and this is one edge, this is one edge, and this is one edge. This we can try and see from the function number of nodes, it says 3, and number of edges. This also gives you the outcome. Now let us try and visually interpret this. Network is all about a graph, right? It's a visualization. So I'll erase this, and to visualize the graph, obviously we need matplotlib library. So I'm installing it or importing it, and then defining the figure template, then defining the layout and the positioning. This is a Spring layout template that we will be using. There are different types of templates that we can experiment for visually representing the graphs. The most ideally or typically used layout is Spring layout. Then I'm using draw NetworkX library to draw the elements of this graph using these properties. The node color will be red, node size is 15. We will have a subplot in this graph that we are defining. And these are the parameters that we are going to pass. This is the template, and we are also going to give you the positioning. So when I run this all together, we would be getting a graph, and we can come here to the plot section, and you can see this visualization. I have not executed this. You can see we have only executed till here, right? So now I'm going to execute the line number 28 as well, and then we will try and visually represent the data once again. So here you will see that 1 and 3 will also be connected if I re-execute this. So depending on what properties we are passing, how the instructions that we are passing on how the network should display the connections between nodes, etc. Based on that, your graph will be displayed here. If I want to also see what are the nodes, not just the number of nodes, but what are those nodes, then we can say g.nodes and convert that output into a list form. You can see 1, 2, 3. Those are the nodes. Likewise, we can do it for the edges. 1 and 2 is one edge, 1 and 3, and 2 and 3. What are the adjacent nodes for the node 1? ADJ basically talks about the adjacent, nearby or neighbors for 1. 1 has 2 and 3 as neighbors, and that's what you will see. When you are going to try and visually represent this for a more complex network, where there could be multiple nodes and we may not have adjacent nodes for certain node, like for example 1, it may not be connected to node 4 or node 5, then you'll not see those nodes as adjacent nodes. What is the degree of a node? Degree is nothing but the number of direct connections. So 1 has 2 direct connections, and hence the degree is 2. This is the property for a node. And here I'm passing 2 and 3. So I'm going to pass 2 nodes, right? So degree view, you can see 2 has 2 connections, whereas 3 has 2 connections. Right? So this way we can pass either one node or multiple nodes to see how many nodes these nodes are directly connected to. If I want to remove any node from the network, you just use remove node 2. So I just remove this node, and if I try and visually represent that, you can see only 1 and 3. I can also remove the connection between 1 and 3. Right? Before that, let me visually represent this. After removing the node 2, this is what you will see. I'm removing the connection between 1 and 3 as well. Remove the edge. Right? Now, if you see the visualization, we will have nodes, but there is no connection at all. So this way we can play around with the network. Now we'll also try and use different visualization methodologies to view the graphs. So here again, we have already imported these 2 libraries. This one, I'm creating a new graph, instant initialization of the graph, and then creating the edges between the nodes. I'm not explicitly defining what nodes I have, but when I define the edge, NetworkX library would automatically interpret that these are the nodes that we have. So I'll execute this. By looking at these commands, you can see that I have nodes 1, 2, 3, 4, 5. Right? So this is my graph. Now, I'll explicitly define the positioning of these nodes. And these are the coordinates 0, 0, minus 1, 0.3, so on and so forth. So I'm defining this positioning. And these are some of the options that we are going to pass for the visualization. So font size, the node size, node color would be black, the edge color should be white, etc. So I'm going to pass the graph G, the coordinates for each node, and then these are the bunch of options that we are going to pass. And then I will try and visually represent this using the matplotlib library. So this is how you can see the graph in a different way altogether. We can also try and visually represent some of the predefined networks in NetworkX library. A lot of examples are there. These examples basically are derived by statisticians who are studying the network data. This is Peterson graph, which, right, again, is something which is predefined. So I'm going to use this Peterson graph to visually represent the data. And you can see this is one way to come up with representation. NX dot draw. Here you can see NX dot draw network. Here it is NX dot draw. With labels, yes, I want to have labels, and I also want the font basically to have bold representation. This is one way. I can pass multiple other parameters. Here I am basically talking about draw shell. This is another function which will allow us to do visualization. And you can see here, there's a little delineation of the representation, right? It looks more like a circlic shape. So this way we can try and visually represent data using different functions. Till now, whatever we have done is an undirected graph. But what if my edges are directed? So here we are coming up with another example. Now this time I'm using digraph. It is not just graph. Here we are defining it as graph, but here it is digraph. Di means directed graph. And these are my nodes 0, 3, 1, 3, 2, 4. So these are nodes starting from 0 till 6. And these are the edges that we are defining for my directed graph. I can directly execute this. This is the visualization, right? Or I can also define like this. This is one more graph that I'm creating. You can ignore this. So once again, I'm defining my empty graph and then defining the nodes. Then we have this assert function, which basically is validating whether this outcome is true or false. So if I just execute from here to here, for me, if I look at the graph, so the node 2, from this definition, I can see that node 2 is directly connected to 1 and 4. So these two becomes my successors, and that is true. So when I run this assert function in Python, assert function is validating whether the output is true or false. If it is true, there's nothing. You cannot see any output. But if it is false, then you'll get error. Assertion error will pop out. Similarly, what are the edges? These are my edges, right? 2, 1, 1, 3. So I'm verifying this also. And the output is true. So what are the number of nodes? From 1 till 4. 1, 2, 3, 4. This is the definition that we are considering, not this one. The number of edges is also 1, 2, 3, 4. Right? Now let us see this graph. Right? The direction is changing. Of course, here and here, because of the definitions that we have given, the graph will change, obviously. So this is your linear directed graph. Now let us come up with the visualization. Again, if I have to consider the visualization for this graph, we have already seen, right? But I want to come up with better visualization options. So I can define the positioning just like what we have defined here. This way. Where should node 1 be pasted? Where should be node 2 be pasted, etc. Right? Like this, I can give the positioning. Or what we're doing here is once my graph is defined, I'm categorizing this into 3 groups. Now my network is being divided into 3 groups. Left side nodes, the right side nodes, and the center nodes. So you can visually interpret that we have 3 layers. This would be left side nodes, the middle nodes, and the right side nodes. On the left side, I'm basically having 0, 1, and 2. This is 3 and 4. And here I have 5 and 6. Right? So that is the representation. You can also see the positioning here. For the left nodes, I'm taking each node in this iterable object. Left nodes is a list. So I'm basically taking each node. for I comma n in this, I'm positioning that n is node 0 will be at the position 0, and then this is I represents the column positioning, right? So you can basically say that you have 0 comma I. Okay, 0, this is 1, this is 2. So left node is at a position 0 comma I is taking from this left nodes the positioning, right? I'll get some positioning here. Then for the middle nodes, I'm basically saying 1 comma I plus 0.5. So whatever the I we are getting here, we are saying if it is 1, for example, 0 comma 1 is this position, then we are saying 1 comma 1.5 somewhere here. So this way we are trying to position our nodes using this 3 lines of code. I'll execute this, categorize them, position them, and I'm also passing the options for visual representation of the graph. And then here I am representing the graph like this. So you can see 0, 1, 2. Then we have 3 and 4, then 5 and 6. Left nodes, right nodes, and middle nodes. Next, we can deal with the graphs in different ways. Here we are basically trying to add an edge called 1 and 2 for the existing graph G. And if I say convert, right, create a digraph, that means convert the existing graph into a directed graph, right? So this way we can also do conversion of graphs into one graph into another one, that is directed graph to undirected or undirected to directed. This is our visualization for H. Okay, so we are putting the directions if you observe here. G is basically taken from here. G is our Peterson graph. So Peterson graph is converted to a directed graph here. Then we can also play around with edges here. The edge list I'm defining 0, 1, 1, 2, 2, 3. And then I'm creating a graph with this edge list, H. Right? These are our edges. And if you look at this graph now, so our directed graph is converted to a undirected graph. Using adjacency dictionary, also we can try and define our graphs. So use this representation and then visually represent your graph like this. If I want to clear all the nodes, then simply say h.clear and you will see that you will not have any nodes or any edges. The elements are getting cleared. Now finally, we have something called as multigraphs in the network. A multigraph is basically nothing but an undirected graph, but there will be multiple edges between any pair of nodes. So when I talk about nodes, right? So for example, here you will see that 1, 2, 3. These are the 3 nodes. So I have one connection between these nodes 1 and 2, 2 and 3. That is what we are defining here. This is the node 1. This is basically the pair. This is node 2. And this is the weightage. So we are also trying to bring in the weightages into the graphs. This is weightage. So you'll have a tuple of 3 elements. First one is the node 1, node 2. 2 nodes have to be represented. And the third one is the weight. So if you look at this definition, we're basically saying that node 1, node 2, 1 and 2. There's a connection and we are putting weight as 1. From node 2 to node 3, I have another graph which is representing the weightage as 0.5 on the weight there, on the edge there. This is like a simple graph. But multigraphs basically means you will have multiple edges between the same pair of nodes. So I have connection between 1 and 2 with a weight of 1.75, and the same connection is also having another weightage which is 0.5, right? So visually you may not be able to see those multiple edges, but when I put this weightages, you will be probably be trying to see the spacing. Okay, the space does not represent the weight, but still, when we try to put it, you may see some variations in the visualization. So here you can see this is 1 and 2 and 2 and 3. Those weightages are given, but size of the edge is remaining same. It's the weight is a different parameter altogether, not the size of the edges here. Don't get confused there. Weightage does not mean the size representation of the edge. It does not mean that. Now, if I try to create a multi-graph with multiple edges between the same pair of nodes, and then if I try to visually represent this, you would see 1 and 2 and 2 and 3. So there are two edges here between 1 and 2. As I said, visually we may not be able to see it, but this is multi-graph. You can also define the dictionary and you can see the total weightages that we have on each node. Because of the connections, we are trying to understand what is the weightage of these nodes. So this is how we can try and work with NetworkX library to define our networks with the elements of a network, that is nodes and edges. Hope you enjoyed the session. Stay safe and thank you so much.